So let us solve this crystallizer example. Aqueous solution of sodium chloride, where it is 70 weight percent of sodium chloride of 2000 kg per hour, and at 30 degrees centigrade 1 atmosphere has to be crystallized. So we have aqueous solution of NaCl over here in 5000 liters crystallizer. The heat duty of the crystallizer, that means the amount of heat that we are providing into the crystallizer to evaporate the water, that is 500 kilowatt, and it operates at atmospheric pressure. The solubility ratio of NaCl in water at 30 degree is 0.4. Now, so we are specifying it at 0.4 because we know our crystallizer operates at 30 degrees centigrade. So it has given only one option, 30 degree centigrade. But if you want to change the temperature, then this information may not be enough. Your result will be erroneous. So it is better to give as much information possible as you can. The particle size distribution function is normal, and with D50, you know what is D50? It is 50% of the particle mass will have the size higher than this. So it is 2.5 centimeter. Okay. And standard deviation is 1.5 centimeter. PSD mesh type is equidistant with 50 intervals between 0 and 10 centimeters. So it has asked you to simulate the process. So for that, we go to our simulation window. So let us go to the properties first. Go to composition. So we have NaCl and water. There is no other component over here. So only sodium chloride and water. But we have to make sure that we have both NaCl in mixed solution and NaCl in solid form. So we have to define NaCl in both of them. So let us use NaCl over here. By default, it will go to the conventional, but we have to make it solid. Okay. And let us give it the names NaCl-S, so that we have a distinction between normal NaCl and solid NaCl. And then again NaCl, conventional. So both are sodium chloride, but one is conventional, the other one is solid. And then lastly water, because we have aqueous solution of NaCl over here. So go to next. Method name, let us use solid because there is no reaction occurring anywhere. So we use solids and run. Okay, so the property run is complete. Go to simulation. We have to specify the stream class. Now the stream class, we have used the conventional, but in the conventional stream, as you know, that it doesn't have any option for solid particles. So we have to change it to mix Cl PSD. Okay. And here you have to have both mixed and Cl PSD. In PSD, you have to specify over here. So what information do we have? We have the information. It is PSD mesh type is equidistance with 50 intervals between 0 and 10 centimeter. So here we say equidistant with 50 intervals between 0 and 10 centimeter and create a PSD mesh. So it is created now. So first let us go to the stream. We have S1 that we have to fix. So go to S1 and the temperature is 30 degree and 1 atmosphere. So it is 30 degree, 1 atmosphere and 2000 kg per hour. The solution is 70 weight percent NaCl, right? 70 weight percent NaCl. So it is 30 degrees centigrade, 1 atmosphere, and it is 2000 kg per hour. NaCl is 0.7 and water will be 0.3. So stream is specified and there is no solid component in the inlet stream, so nothing to fix over there. Now go to the setup. So many things have to be done. Okay, so temperature operating condition, let us run it at 30 degrees centigrade and pressure 1 atmosphere. So it is okay. The information is different. Actually, it is not operating at 30 degree. It is operating at 500 kilowatt heat duty. So we have to give this information. So our system is not actually operating at 30 degrees centigrade. Okay. So the solubility ratio of 30 degree information will not hold over here. So we have to give some extra information. Anyway, so you have to give 500 kilowatt information over there. So we go back to heat duty and 500 kilowatt. Yeah, so it is 500 kilowatt. And solubility data we have to provide. Now here the solubility data. So as per the problem, we have 30 degree and 0.4. Okay, so this is the information that we have as per the problem, but as I explained that we have not fixed the temperature of the crystallizer at 30 degrees centigrade. Rather, we have given the heat duty, so temperature is variable. Now we do not know at what temperature it will operate, so we have to give some more information to that. So we really cannot work with only one temperature. The result will be erroneous. So let us give as much as information as possible. For that, we go back to our data that we already have over here. So let us open an Excel file. and add these values. So it is 298.15, 303.15, 313.15, 318.15. No, 318.15 we do not have any data, so we do not have to give it. So we go to 323.15. So it is 323.15. Then again we drop 328, directly go to 333.15 and 343.15, 348.15, and the last one is 353.15. And the NaCl data are 26.483, then 26.550, 26.701, 26.889, 27.106, 27.338, 27.478, and finally 27.602. So these are the data points that we have, and we have to work with the information as per the requirement. So we have to find the ratio, right? So to find the ratio at, first we convert this Kelvin to centigrade. So each and every temperature we subtract 273.15 from it. So it is 25 degrees centigrade, and here, so the ratio is in 100 grams of solution we have 26.483 grams of solute. So we do not have to change anything. Only thing is that if you change it to solvent, then you have to find the ratio for that matter. So we can directly use these. So for that we just copy these numbers and we place over here, just make a copy, and then we have to divide it by 100. Okay, so the ratio will be like this. So copy it and then place it over here. Yeah, now it is done. So we have fixed the ratio at various temperatures starting from 25 degrees centigrade to 80 degrees centigrade. The crystallization, what is the reactant? Reactant is the NaCl. Okay, NaCl will form into NaClS. So NaCl with it is decreasing to product NaClS. So this is the product. It means that NaCl is converting to NaCl solid. So that's what it means. Okay, this is a stoichiometry. So this is done. Let us not use any recirculation. We can directly go to particle size distribution. For the time being, let us use the particle size distribution, whatever in the example it is said, it is normal with D50 2.5 and standard deviation 1.5. So it is D50, the standard deviation is D50 is 2.5 centimeter, standard deviation 1.5 centimeter. So it is 2.5 centimeter. Actually, I am doubtful about the example problem that has been given elsewhere, because 2.5 centimeter salt particle is quite big. I do not know how the simulation will come. It is again centimeter, 1.5 standard deviation. Okay. And crystallizer volume also we have to fix. It is 5,000 liters. So it is 5,000 liters. And we can run the simulation. Okay. So here you can see the stream result. Out of 2000 kg per hour, we'll give a name so that we can understand it better. Say it is feed. This is vapor. And this is the product, solid product. So out of 2000 kg per hour feed, we get 1398.71 kg per hour of product, and 601 kg per hour water will be vaporized. Obviously, in the water, there will be a small NaCl component as well, but mostly it will be water. And in the product, there will be negligible water. It will be mostly the solid particle and to some extent the liquid NaCl that will be moist. Okay. And if you want to see the particle size distribution, then we go to the stream and you will find both mixed substream and CL-PSD substream. Here you can see the CL-PSD substream, and here you get the PSD. So this is the PSD you have, 0.2 centimeter, it is like this, 0.4 centimeter. So this is the fraction of particle size that falls in the range of 0 to 0.2 centimeter, then 0.4 centimeter, 0.4 to 0.6 centimeter, and so on. In equidistant way, it goes up to 9.8 centimeter to 10 centimeter. It's like this. So if you want to see the particle size distribution, you can watch over here. Press OK. So this is the particle size distribution we have. Okay. Now let us change our simulation a bit. Instead of go back to the setup. Here, instead of the instead of user specified growth, let us use the particle size growth kinetics crystal growth. Okay, and for that we need the information from Perry's handbook, and here we will take this example. Let us take this example, Asserberg's PhD thesis. So in our case, KB will be 1.92 e to the power 10. So it will be 1.92 E10. And then IJK, I will be 2, J will be 1, and K will be 2. So 2, 1, 2. So it will be 2, 1, 2. So this time we are not using the user specified PSD, but we are using PSD from growth kinetics. And let us run it. Okay, so it has run. Now go to the stream and we find the PSD average. So now you can see it is a bit different. We will compare with the earlier one. First, let us see how different it is. In this case, you can see the particle size distribution, how it looks. And we will compare it with the previous one. For that, we go back to the PSD, the user specified, the old one, run it. Okay, and go to the stream once again. Oh, so this is the result summary we have got. And go back to our particle size distribution and see how it looks like. So this is our previous one with the crystal growth, particle size dynamics with crystal growth. And this is the user specified particle size distribution. So how it changes. So with this small example, we can check how the particle size distribution changes by the choice of the calculation method. Okay. So with that, we come to the end of this lecture. Thank you.